Hi, everyone. My name is John Stewart. I'm a managing director at Aon Cyber Solutions / maybe Strauss Friedberg, featuring Strauss Friedberg. And I've been a digital forensics developer for 20 years now and lead a development team at Strauss, building internal forensics tools. I, by sheer luck, got my start in forensics interviewing at this startup that was like 3 blocks away from my house named Guidance Software, and worked on Ncase. If you've ever had an Nscript crash on you, that's probably my fault. I'm sorry. This is my penance. So we're very, very excited to talk with you about Llama and forensics file processing.
And I'm Julia. I'm a software developer on John's team. Some projects that I worked on this past year were a IOC lookup service and a timeline web viewer. But for the last few months, the main thing I've been working on is Llama. So we're excited to share that with you.
So Llama, actually, fun fact, it has nothing to do with generative AI. I've actually been working on this for like years, just off and on. I started in 2019, and it stands for Llama is LightGrep's amazing media analyzer. But then there was like this pandemic, and all of a sudden, like everyone was getting hit with ransomware all the time. And so had to take a couple of years of like putting this on ice to address that. Also, there was another pandemic at the same time, so that was fun. That's what we're going to be talking about. My shaggy dog story is to ask you, how did French cuisine become like sort of like the gold standard, at least during the 20th century, most of the 20th century, for like fine dining and cooking? And the answer is there was this like celebrity chef back at like the late 1800s, early 1900s, Auguste Escoffier. And he was a famous French chef in Paris. He got recruited to the Savoy Hotel in London and like the Savoy became the greatest restaurant in the world, the place to eat where everybody went. But he wasn't just like a great chef. He wrote cookbooks, and he thought about like what were the essentials of French cuisine. And of course, it's the sauces. And he went through all of the sauces that were in French cuisine, and he boiled them down, like distilled them into like saying there are 5 basic sauces or essential sauces from which all the others derive. And those are what he called the mother sauces. So it's like velouté, bechamel, sauce tomate, tomato sauce, hollandaise, and espagnole are the mother sauces. And he wrote these in his cookbooks, and it was because of his cookbooks that like French cuisine was able to replicate around the world. That is my terrible analogy for forensic file processing. So the basics, right? Like this is stuff that like everyone probably knows here. If you've ever worked with an evidence file, you know these things. You know how to filter by your file system metadata. You know how to do file signature analysis. You know how to do hashing and hash set analysis. You know how to do pattern searching, keyword searching. And of course, you're familiar with the pain that's like, oh, now I have to mount all these archive files, right? But these are like the essential ingredients and the operations that we perform when we're doing forensic file processing. And because they are so fundamental, I think it's worth paying some attention to them, even if they are kind of solve problems in the tools that we use. So let's go on to the next slide. So my job is to provide automation at scale for forensic examiners. And these operations work pretty well in the GUI tool of your choice, whether it's Ncase or the German version of Ncase, which is Xways, or Axiom, and Autopsy, right? Like you can do all these things in there, and they're actually not that hard to do. Like they each have their own little way of doing it. And you can sort of chain them together and go from one to the next, and right click and blue check and all that kind of good stuff. But automation at scale isn't really possible with the current crop of GUI tools that we have for forensics. And so when we talk about automation at scale, we're talking about command line tools. And that's totally different. And I don't know of an easy way, of a good way to do these operations automatically on the command line at scale, right? Like batching up like hundreds of evidence files or collections or that kind of thing. Like, we have like our Lightgrip tool that can search like a file, but it doesn't search an evidence file. And, files like, they're like, unless you're HAL and you can just like Pomeranz, you can just like roll off like, command line pipelines without thinking about it. This is like really hard stuff to do. It is not easy. And I'm not HAL, so it's hard for me too. So that's what we're trying to do with Llama, is bring these operations together into one command line tool. We're going to talk about these operations. So first up, file system metadata. We don't really have to talk a lot about this, right? Like the answer to this is pretty simple. You take the file system metadata and you put it in a database and then you can query it. It's easy, it's fast, no problem. Llama uses the sleuth kit, which is the open source forensics file system parsing library. And so we kind of follow the sleuth kits model for that. Two important points here of how we treat file system metadata though. The first is timestamps. I work with a lot of amazing examiners and most of them are able to script their way through things. And so I tend to think of my job as not really having to do like a ton of scripting, but it's more about testing and ensuring that we get our time zones correct and that we get Unicode and our encodings correct, right? Like that's my job, is to make sure that we get those details. And timestamps are really hard. So most of the libraries and the tools that you use, like their precision, that like all the default date time libraries that are out there, their precision is limited to milliseconds. But NTFS file times are in hundreds of nanoseconds, right? So your tools that are probably using like those standard libraries that like everything uses, they're actually probably missing out on that precision. And that's why I think that the best format for storing timestamps are strings, which sounds silly and wasteful and terrible. But that is what I believe, because the ISO 8601 format has some very nice properties. And then we store all of our timestamps in that format as strings. One of the nice things about it is that you can keep adding on precision. Just like you could do hundreds of nanoseconds. You could go to nanoseconds if you had it. Like it works. And things will still sort correctly. Even if you have timestamps with different levels of precision, your sorting will work out well with that ISO 8601 format. The other thing we do with timestamps is they're always in UTC, right? Like I have a new computer now. My old computer, I want to like Phil's stickers on it that said UTC or GTFO, right? Like everything's got to be UTC all the time. Second important thing about file system metadata is you don't want to put we tend to think of like file entry tables, right? Like file, 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 file. That's not actually how file systems work. Most file systems have two important structures: the directory entries, which are your path hierarchy, your folder hierarchy, and then your inode table, which is more like an MFT. An MFT is like a weird inode table that also has the file names in it. But there's also directory entries in NTFS. Those are your $I30, the index buffers. Those actually act sort of as directory entries, the way other Unix file systems work. And the reason that's important is because of hard links. So if you get like a time machine backup, right, and you try to process that in a normal tool, it's seeing duplicate after duplicate directory entry after duplicate directory entry. And the naive way of processing them will like, it will like the sun will go supernova before that ever happens, right? Before you're finished processing. So you really need to treat those two things separately and dedupe on the inodes so that you're not reprocessing duplicate files.
All right, next, mother sauce, file signature analysis. So most of you know that this is an important part of forensic file processing, and it's baked into Llama. So the way that we're doing it is we have this file called magics.json, and within this file, we have over 900 different file records that each correspond to a unique file signature. It's powered by LikeGrep, which I won't go into now, but we'll talk a little bit more about that on the pattern search slide. But I know it's super tiny, so you can't really see it, but each of these file records contains, among other fields, a unique ID for that signature, the pattern, so AKA the magic bytes, a friendly name that our team came up with for each file type. Shout out Shane if you're watching. And then also a list of extensions that are associated with that file type. So not only can Llama help you identify a file by those magic bytes, but it can also tell you whether there's an extension mismatch, right? Because if there is, if the magic bytes are telling you one thing, extensions telling you another, maybe there's something amiss.
So hashing. I hope that you all love hashing. It's not really too much to talk about with hashing here, but I do have two things. The first is that not all hash algorithms are created equal. And there's a new one on the block. It's not that new, it's several years old now. And I really wish that all of our tools used it. It's called Blake3. It's a 256-bit hash. So it's pretty strong. It's got a lot of bit length. There's no known attacks against it. It's not quite as strong as SHA-256 when it comes to like using it for cryptography. But for like file identification, it's great. And the thing that's really great about it is like it's 6 times faster than every other hashing algorithm. So we should very much be using Blake3. I think probably a lot of you think that, oh, hashing is not that slow, but actually hashing is really slow because it's got to do like a lot of operations per every byte. So Llama has Blake3 built in. That's our default hash for a lot of things. Of course, we'll work with other hashing algorithms too, but trying to like push Blake3. Second thing is hash sets. NCase had like that old .hash hash set file format. I don't know whether that's changed at all in the years. I haven't used it in a long time. But it's actually like a good idea to have a binary hash set format. I think for interchange and download, text-based formats are great, or like the database that NSRL distributes now that they're distributing a SQLite database. Those are great formats for interchanging stuff, but they're too slow for looking up hashes and doing the hash set analysis. So we've designed our own hash set file format called hset. And hset is a binary file format, works similar to like the .hash file format in NCase, except it's like algorithm agnostic, right? It can store like hashes for lots of different algorithms in it, has like the ability to have metadata in it, the ability to store file sizes in it as well. So it's kind of like a more modern format for that. And then it really optimizes our hash set analysis capabilities.
Okay, I said I would get to this. So pattern search, another mother sauce. What is this, hollandaise? I don't know. So pattern search is powered by LikeGrep. And I'm actually curious, who here has used LikeGrep before? Okay, nice. Well, anyways, those of you who may not know what it is, it's a regex engine that was written specifically for digital forensics. It supports over 100 encodings. It can handle thousands of patterns, so it's a multi-pattern regex engine. And the way it works is it does one single pass over your input. So it's super fast. And then it's also easy to learn if you already know grep, because it does support a subset of that standard grep syntax. If you want to know a little bit more details about how exactly this works, maybe we can talk later, but high level, LikeGrep will smush all your patterns together into a ball of logic, which computer scientists like to call deterministic finite automata.
Yes.
So yeah, okay.
Okay, and then finally, archives. I would say this is the Espanol sauce because it's impossible to get right. I tried to make an Espanol sauce once like 10 years ago and it was awful. Like wasted a day on it. Not to mention like so much money. So archives are terrible and they'll break your heart. Llama, like we're not there yet with the archive support, but we're working on it. And the way that we're working on it is with, there's an open source library called libarchive. Libarchive aggregates a lot of different libraries together to support a large variety of different archive file formats. So zip, tar, rar, 7-zip, like CPIO, lots of old ones, and a lot of compression algorithms as well, including XZ. LibArchive was actually one of the targets of the Geotan supply chain attack earlier this summer. Fortunately, didn't get in, so that was good. It didn't get into LibArchive, but it's a pretty solid open source library, and we've been using it in our own forensic file processing framework internally for many years now, and it's worked very well for us. An important thing with archives is when you're processing archives is you really want to have hash sets while you do that. Because if you've got the NSRL or other hash sets that you can use for exclusion purposes, you're going to, some proportion of the archives that you run into are going to be well known. Those might be larger archives, right? Like open source libraries. Like if you've ever had to investigate a Java developer's system, that's always terrible because it's strewn with duplicate jar files all over the place, which are of course just zip files. So your file system tools will start expanding them over and over and over again. If you can eliminate duplicate archives, it will really speed your file processing times. The other thing, of course, is you just want to have hash deduplication in there too, so that you're not processing duplicate files regardless, because archives tend to propagate themselves all over. So important kind of tip with archives. So these 5 different aspects of file processing, these basic operations with forensic file processing, they have a lot of options. But the data flow pipeline that we've defined in Llama is always the same. So we start out getting our directory entries from our doing a recursive descent to the file system. From our directory entries, we're able to get the inodes. From there, we can filter and dedupe out by the file system metadata, as well as dedupe on the inode number, so we're not reprocessing the same inodes over and over again, all still while preserving the original directory entries. Then you'll want to do file signature analysis, because with file signature analysis, yes, you have to open the file and read some data out of it, but you only have to read a little bit of data out of it to determine what kind of file type it is. From there, hashing it, that's going to read the whole file, but optimistically, hash it first with 3, because that's so fast, and then see whether it's a duplicate. On the off chance that it's a duplicate, then you don't have to do anything else. You've already processed that content. You just have to remember what results you had for that content before. From there, you want to do the rest of your other hash algorithms and do your hash set matching, and then go on to pattern search. And then, of course, there's the archive recursion, and that's the terrible part, because not only do you have to then mount expand the archive, but then every file within there has to go through this queue over again, and you have to manage it and the error recovery. That's why archives are hard. And of course, your metadata that gets all screwed up then, right? Because every file format, archive format uses totally different metadata. And so how do you synchronize that with your own conception of file system metadata? Finally, you save the results off to a database. That's the Llama pipeline for our data processing. So next slide. So there, I was working on this for years and kind of dithering about it. And there are 2 things that recently happened that made me made me excited to work on this tool and really get it done and ship it. The first is for a long time, I was putting all the results out to JSON, and it's terrible, actually. We tend to think JSON, oh, it's easy, but no, it's you get lots of duplicate output, then you have to parse it. Parsing it is it's not hard, but it's not fun either. It's a little better than parsing XML, not a lot. And it's big. And so I found this library called DuckDB. And DuckDB is like SQLite, where it's an embedded library. But whereas SQLite stores records all together, it says one record and then your second record and your third record, DuckDB is a columnar database. So it takes all of the values for one column, stores them together, all of the values for another column, and stores those together on disk. So reassembling the record takes a little bit more time. You got to like search and stuff. But it's actually one of the things that's nice about it is you get the benefit of compression algorithms then operating on column values that are all very similar to each other, as well as like some vectorization, like using the vector units on your CPUs. And then you also get the benefit of not having to create indices, because by grouping all the column values together, if you have complicated where clauses and you're doing joins and like lots of table scans, operating columnarly, it's kind of like you have an index on every single column without having to pay for it. It's not quite as good as an index, but it's pretty close and it ends up paying off. And then in terms of on-disk representation, there's an open source format that DuckDB works with called Apache Parquet. One of the nice things about Apache Parquet, there are a lot of open source tools that use it. It's been around for a decade plus. But if you upload it to S3, Amazon, if there are any Amazon users, S3 storage is pretty cheap. And AWS Athena, which is like this on-the-fly database engine, serverless database engine for like querying CSV files or JSON files that you have in S3, it can also work with Parquet. And it's like 9 times faster when you work with a Parquet file as opposed to CSV or JSON file in Athena. So your queries are much faster. You can scale like amazingly. So you could have like terabytes and terabytes of these things, and you're still getting query response times back in like a minute. Because the Amazon just like scales across all your partitions and stuff, and it's amazing. So that's our output format, is just like writing to a DuckDB format on Parquet files on disk. So this is a blast from the past. In 2007, 2006, I created this dialog box that you see here before you as part of an end script called the evidence file processor that was like $1 million end script that Guidance sold. I spent like months working on this dialog box, and it allowed me to specify end case conditions on your file system metadata, keywords, and hash values all together in like complex logic. But this is the problem with the command line tools that don't get the benefit of a dialog box. Like, I mean, this isn't like the world's greatest dialog box, but it's better than like having like 30 million command line switches. So this is the thing with Llama where I'm really kind of puzzled on how we should allow you to like put in all the options and control all the logic. And that's been one of the things that's been kind of a hang up for me.
John, don't even worry. Don't even worry about it, because I actually wrote a rule language for it that's kind of like Yara, but for Llama.
You wrote a rule language?
Well, like, it's hard. It was kind of hard.
Okay, rule language.
No, what's funny is I tried to do this initially with Antler, and I remember I was having a little trouble, and John comes up to me, he's like, oh, why don't you just write your own recursive descent parser? I was like, yeah, why don't I just do that? Anyways, okay, so I want to take you all through an example Llama rule. So those of you that are familiar with Yara will probably recognize a few of these, but you'll notice that there's a few more sections, right? So we're going to go through this step by step. So it starts the same as a Yara rule, right? You have the rule keyword, the rule name, and then everything else is enclosed in curly braces. And then you have the meta section, which is the same as Yara. It's just arbitrary key value pairs that are not actually evaluated by Llama, but they provide some more context to either future you or someone else that might be using your rule. So like a description, or you can sign it as the author, the date it was created, etc. There's this file metadata section. Within this section, we have some reserved keywords. So you can filter on file attributes such as created time, modified time, file size, which you can do in Yara, by the way, file name, and file path. So quick callback to what John said, but you'll notice that those timestamps or those dates are in, they're a string, but they do have to be in ISO format. Yeah, it's a little caveat there. Okay, so this next section, I I'm using a different rule. And the reason why is because as it works now, Llama will implicitly and every section. So if you have a hash section, there's not really a point in having any other sections, because if that one fails, then what's the point, right, of having those other sections? But anyways, all that to say, there's also a hash section in a Llama rule. And this section will support MD5, SHA-1, SHA-256, and Blake3. And then that I didn't show in this example is that you can also comma separate these hash values. So you could do, you know, SHA-1 equals whatever, comma, MD5 equals whatever hash value. And what that implies to Llama is that both of those things have to be true for the same file. So maybe you're worried about the rare hash collision. That's going to be something that you can double check with another hash value. All right, next section is the signature section. So you'll remember what I said about file signature analysis and that magics.json file. But the two fields that we're supporting currently in the signature section is ID, which is going to be like that unique ID from magics.json, and the friendly name that's in each record. The difference between the two is going to be that some file types are going to have the same friendly name. So certain archives will have the same, will have different patterns, but they still are the same file type. So if you want something a little more granular and you want a very specific file record, then that's when you would use the unique ID, if that makes sense. All right, this next section is the grep section, and this is probably what you will find most familiar to Yara. The only difference is we've moved it up a little bit, so there's subsections now, and then that string section is patterns. So the grep section in Llama has two subsections. The first one is the pattern section, and for each pattern, there are different pattern modifiers that you can add on to the end. So you have fixed, which will interpret that string as a fixed string, because by default, Llama is going to interpret all the patterns as regex. So keep that in mind. You can also say no case for case and sensitivity. And then it's not on here, but you can also do an encodings list. So you can do encodings equals UTF-8, UTF-16LE, whatever you'd like to put there. Okay, so that's the pattern section. And then we have the condition section. So, turn my mic off. Hello, hello, can you hear me? Okay. The condition section is going to look a little bit different from Yara. Instead of having those, like, you know, 4 of them syntax, we do this with functions. So this one in particular is called count has hits. And what that's saying is that, okay, I'm giving you 4 arguments that are pattern identifiers, and I need at least 3 of them to have at least 1 hit. Bear with me. I'm going to go through each of the functions super quick. So we have any that works very similar to its Yara equivalent, but it's basically saying if any of these patterns that I've provided in my arguments have at least 1 hit, then I'm going to return true. And then the same goes for all. Except it returns true if all of them have at least 1 hit. Count is gonna verify the number of hits for a pattern, and then count has hits, as I already explained it. Sorry, I'm trying to move fast. Length is going to verify the length of your hit. So if you have like a wildcard in your pattern, and so you can have a variable length for your hits, and maybe you want to verify the length, you can do so with this function. And then lastly, the function is for when you want a little bit more control over that hit. So you want to say, okay, I want the hit of the 5th hit of this pattern to be at least at this byte offset, for example. So it just gives you a little bit more granular control over that hit.
Okay, are we able to get the input switched over? Let's see whether that works.
Yeah.
Oh, perfect. Okay, so to save a little bit of time, I went ahead and ran Llama while Julia was speaking, so we don't have to wait for it to process here. But this just ran, and I processed the Sans and Fury training image that we like to use at Straws for a lot of our internal testing of our own tools. And looks like I'm getting a little clipped there.
You're good. You're good on the screen.
Okay, perfect. But the overall time that it took to process this evidence file was 113 seconds. It took 359 seconds of CPU time, but got lots of scores. That's a good thing. But it, less than 2 minutes to hash this training image. The small training image, but let's see what we've got. Try to make sure that I don't mess up my HDMI here.
Everyone pray to the demo gods.
Our output gets put into a new directory that I just specified here on the command line called out and fury. And this is what a Parquet database looks like. It's a directory and it has one Parquet file per table. And those tables are named after, just on the file name right there. What's also nice is that it comes with the schema.sql file and a load.sql file. So we can actually run DuckDB from the command line here. And then I can just say out and fury schema.sql. And it's going to recreate the schema inside of DuckDB. And then it's going to load it. And then we can say select count star from Durant, 216,000 directory entries. Let's do Durant.path. inode created. Hash.shaw 256. And we'll join it. On the inode number. And of course we should sort, right? And let's limit ourselves to 5. Well, oh. Convert string to UN64. Oh, did I mess it up? Oh, the demo gods. They were unhappy with me. We'll skip hashing. So, we can just get instant queries like that with DuckDB. It is so fast. It's awesome. So, I don't know, will you have enough time for probably not another demo? We wanted to show you a rule demo with a cool piece of malware that one of our colleagues, Zach Reichert, just found. It's a cool Linux malware that he wrote about on our the Aon Cyber Solutions blog just on Wednesday, where it's hooking UDEV device entries as a persistence mechanism. So that's a fun thing. But we should go on back to the slides. So roadmap, Llama is a proof of concept at this state. We're open sourcing it, it's going up, but it's early days. So there's a lot that we're going to do, but it's going to be the new engine for our own internal forensics file processing framework. So we're very committed to it. And we're here to tell you about it because we want your feedback. We want your help testing it. We want people who are interested in screwing around with it. And we also want to just lots and lots of feedback. In terms of roadmap, I like to take good ideas from other good tools when they have them. So I love the HTML reports that Hayabusa makes. I want to make HTML reports out of Llama too, so you're not having to query DuckDB on the command line like that. I think that would be probably useful for most people. We're also committed to foundational libraries in open source. So last year we released a registry library called Metadata. We released Cider, which did Windows search indexes. Julie talked about that. We've got a new library coming out for reading EO1 files written from scratch in Rust. We have to do a lot of QA on it. We're not going to ship it. We're not going to ship it an EO1 library early without much testing. We're going to do a lot of testing on it, but I'm very much looking forward to that because I think it's going to significantly improve performance of reading EO1 files, as well as like we also have a VMDK library, so we can do VM images too. We want to extend the rule language so that it can handle parsed artifacts and other file formats. And then I really like the idea of being able to pair rules with different actions. So having like a set number of actions that you could perform and say, you know, when you get this rule, then perform this action, like copy this thing out or run the shell command or wipe this file if it's on a live system so you could do remediation. So that's sort of like what we're thinking about in terms of future features.
Okay, last thing, super quick. I just want to echo what John said about wanting your feedback because like we said, it's still very much in beta mode. And if you have any feedback on the syntax of the rule language, I in particular would love to hear what you have to say. So anything that would make it easier for you. And if there's anything that we talked about and you were like, oh my God, I wish it could do this one other thing, let us know. It's still in development, obviously. So yeah, just come up and talk to us and open up an MR, open up an issue in GitHub once we put it up there.
Oh, it's public now.
Oh, it's public.
Yeah.
Great. All right, it's up there. Oh yeah, and it's Apache 2.0 license, so it's actual open source.
That's it. Thank you very much.